Yes. Welcome to our N3AS seminar. Today we are very pleased to have Nicola Franchini. He will be talking about black hole perturbations. Over to you, Nicola.
Okay, so hello everybody. The topic of the talk is based on this. Can you see my arrow? Yeah, it's a bit slow maybe. But yeah, these three works I've done in the last year in collaboration with Sebastian, Enrico, and Emanuele, where the aim is to study the reconstruction of the perturbation potential of a black hole using quasi-normal modes. So first of all, we are focusing on black hole ring down, which is the last part of the in-spiral merger and ring down, as it's called, of a black hole binary merger. And so as you can see, it's this last part here on the right of the signal. And it's where you have one black hole left that is relaxing to a stationary state. And this relaxation with emission of gravitational waves is described by perturbation theory. And since now with LIGO, Virgo, and Kagra in the next observing run, we will increase the sensitivity in seeing gravitational waves. It will be possible to actually do like deep test of general relativity using the ring down only part. And this is interesting because from perturbation theory in general relativity tells that this signal is determined only by the mass and the spin of the black hole. So if you find some divergence from this hypothesis, you're actually challenging the no-hair theorem, which is one of the fundamental results of general relativity. So, as I said, this signal here can be seen as a superposition of damped sinusoids. So these frequencies here appearing, they're complex, and it's a set of, it's an infinite set of frequencies, but of course, depending on the amplitude and the decay time, only some of them are visible. And as I said, in GR, they're determined by the mass and by the spin. And this is true in general relativity, but what happens when we go in alternative theories of gravity? So the things that can be different beyond general relativity is that, first of all, the background metric might be different, might not be Schwarzschild or Kerr. So there are what's so-called additional presence of charges, or what is called hair. But then also the dynamics. So the background metric can be the same, but the dynamics can be different. So the way how the equations are built, they have some additional interactions that are modifying how the gravitational waves are produced and emitted. And then there can be new fields that are coupling to gravity, for example, scalar or vector fields, that can interfere in the production of gravitational waves. And then also what is that? The message you can set up in, okay. And also because a black hole in general relativity is determined by observing surface, so the event horizon, but in alternative theories, this might not be the case. So there are cases studied in the literature. And the focus of this talk will be on the first 3 points, that all of them, they are actually changing the perturbation equation, whereas the last one is changing the boundary conditions. So it can be addressed, but in a different way. Instead, these 3 points, they can all be taken in the same way. So first of all, I want to recall how black hole ring down is studied in GR. So in spherical symmetry, there is this master equation as like a Schrödinger-like equation, where here I denote with this function f, a function that goes to 0 on the event horizon of the black hole, which is determined by RH. And it's a second order differential equation of this variable phi with some eigenstates, the eigenfrequencies that are determined once one imposes the right boundary conditions. And the dynamics is actually determined by this effective potential that can change depending on what perturbation we're looking at. So for example, for a Schwarzschild black hole, for odd parity tensor perturbation, so perturbations of the metric that transform as like a magnetic field, the potential has this form, whereas the other parity perturbations, they have the so-called Zerilli potential. You see they have slightly different forms. So you can put them back in the equation and compute the frequencies. So how would you change this equation to take into account beyond GR effects? So the scope of this talk is to change being agnostic on the theory. So if you don't know what your theory is, you still want to capture as many deviations as possible. So here you might have noticed that I added, first of all, more fields that are coupled together by this Bij. So before we had only one field phi, but now we can have coupling among other fields. So this is taking into account potential scalar fields or vector fields that are interacting with our gravitational field. And also now, the potential becomes a matrix. And this matrix has some diagonal components that will be the GR components, but then modifications that we are actually writing in this 1/r basis. So there are these alpha terms, which are just numbers. And then you can relate these alpha coefficients to the theory that you want. For example, I don't know, you can do it for Einstein-Dilaton Gauss-Bonnet, dynamical Chern-Simons, a lot of Hordensky theories. So a broad class of theories can be mapped to these alphas. And then at some point you truncate, of course, the sum is not infinite, but you try to mimic all the possible deviations in this 1/r basis. And actually these alphas, we saw that they can be linked with changes to the metric. So you can actually, because these are dynamical terms, but you can actually link it to the background metric. Okay, so once we have this, we assume that the alphas are small quantities, and then we can do this formal expansion in alpha for the frequency. So we can expand around the GR frequency and compute these first order and second order coefficients. And these coefficients are universal, they don't depend on the theory, because all the theory is captured by the alphas. And they just depend on the overtone number, so the number of nodes of the mode with respect to the r direction, and the angular momentum.
Nicola, can you wait for 1 minute? Because there is a question by George. So George, can you please unmute yourself and ask your question?
Yeah, hi, thank you. Could you go back to the previous slide?
This one?
I'm just wondering, if I take the weak field limit, so just try to linearize everything so that Vij/Gr is, weak field, and then the Fs are just in that upper equation are just 1. And then I just get the usual kind of wave equation we'd expect in linearized gravitation, correct?
Yes.
And then when you, but this is fully general. I mean, so you can have the nonlinear terms in Vij/Gr.
Yes.
Right, and then I'm just
no, but this is like linearized gravity. This is already linearized gravity. I mean, to get this equation.
All right, but if I take the linear regime though, if I take the weak field limit, then those Fs are just unity, I think, and I just usual kind of quadrupole radiation, plane waves basically as solutions. But then I'm just wondering where the nonlinearity comes in. So you can certainly put it in Vij/Gr, but the higher order terms I also couple in the nonlinear effects, I think through F. Is that correct?
I think we're talking about two different things.
Sorry, go ahead.
No, yeah. I mean, in the sense that these terms that I'm adding here on the right, they're just corrections to general relativity. And it doesn't matter if it's like weak field or not weak field. And all this framework, you find it once you linearize your equations of motion. Okay. And then, so you can also perform like a weak field limit on the linearized equations.
We're already in the weak field.
Yeah, but I would say that all these terms would disappear in the weak field limit because alpha actually has some in general, it has some scaling.
Very good.
With
yeah, so I see that if I can impose the weak field limit on top of this, but
yeah.
this actually, although it's linearized, it still has many of the features of the nonlinearity. That's all I'm asking.
Yeah.
Yeah, very good. Thank you.
You're welcome. Yeah, so what I was saying, yeah, these coefficients are actually quite powerful because they're universal. So once you fix the Overton number, the angular momentum, and the field content, so I don't know, polar perturbation for the metric, then they're set. You can compute them once for all, and then you specify your theory, and you get your quasi-normal modes. And this was done in these two papers here in 2019, and then we extended it, computing the coefficients for different Overton numbers. Like here, you can see like dk, it's a real part versus the imaginary part for different Overtons. So each color is a different Overton, and each point here it's labeled by the k coefficient. So you can see that as you increase with the Overton, these are actually growing, and you can link it with some instability that has been found with other methods for the Overtons when there is some external perturbation. Okay, so once we have this, the idea that drove us throughout these projects is like try to address the so-called inverse problem. So like, suppose that in the future, we will detect some deviation from general relativity in the ring down. Can we actually trace back what is the potential and eventually the coupling from the metric with other fields that actually originated this deviation? Okay, so to answer this question, we actually used a Bayesian approach. So assume that we have some set of parameters, theta, in this case, it will be the alphas coefficients, and some of observables, so some frequencies that are detected. We can link the distribution of the parameters theta given the data observed using the Bayes formula that connects the posterior to the likelihood of the data given some parameters and the distribution of the prior that we assume for the parameters divided by the evidence of the data. Okay, and so in the end, what matters here for reconstructing the posterior is like the proportionality between the left-hand side and the numerator in the right-hand side. So what we really care about is how to determine the likelihood. Okay, here we assume like a Gaussian likelihood where of this form here, where the vector h is nothing but the difference between the data that we assume that we will see. So we actually inject some numerical frequencies minus our model, and our model is the frequencies omega that depend on the set of parameters alpha that we want to infer. And here it's just a rescaling because we don't know what is our h, so we rescale it by its value in general relativity. Okay, and then we need to multiply it by the covariance matrix, so that takes into account if there is some correlation between different modes. Okay, so once we do this, so the first thing we checked is through this principal component analysis to reconstruct the potential, injecting this set of alpha k, or for k being from 0 to 7, for some axial quasi-normal modes and L equal 2. And here in the plot, so you can see the reconstruction with respect to x. X is just a compactified coordinate. So 0 corresponds to the horizon and 1 corresponds to infinity. And you see, so the black line is the injection that we assume that we will measure in the future. And then the different color are the 2 sigma distance from the reconstruction. The green one is assuming that we see only one mode, the fundamental, L equal 2 mode. And then the orange line is that if we assume to see the fundamental and the first overtone, and the blue line if we also see a second overtone. So you see that increasing the number of observables, you get closer and closer to the injection line. So we are actually able to reconstruct that there is a deviation, because the 0 is general relativity, and the deviation is actually well detected, and it's well approximated if many tones have been seen. And this can be a problem because it will not be really easy to observe quasi-normal modes. There is some debate ongoing in the community. So, but at least I can say that we can kind of reconstruct the potential, but there are some caveats. For example, I didn't show all the plots, but here it was like very optimistic for the errors and so on and so forth. So if you try to do some more realistic things, it will be more difficult to reconstruct properly. But in principle, there is a way to do it. Now, the next question is, from the reconstruction, are we actually able to put constraints on the single values of alpha, so the single components of the effective potential in 1 over r? So the way to do it, so remember that this is the deviation, so each alpha corresponds to a 1 over r to the k power modification. So we can try at the same time to do an optimistic case when we vary only one parameter at the time, and we try to reconstruct that, knowing that all the others are not affecting the potential. Or the pessimistic case, it's when we vary all of them at the same time. So, and here in these plots, I'm showing you each of the bands correspond to trying to put a bound on a single alpha, so alpha 0, alpha 1, alpha 2, alpha 3, up to alpha 10. The left side of each panel will show the optimistic case, and the right side only the pessimistic. And the red bands are the injections for each of the alpha. So you see that all of the alphas are 0, except for the injected alpha are 0, except for alpha 2 and alpha 3. And the different colors, so blue and orange, are just a different prior, a different choice for the priors. So, and actually the choice of the prior shouldn't affect the posterior, but here you see that it is really affecting, and it's very uninformative. So it means that we are not able to constrain the single alphas. But so is there some more clever parameterization that we can use to actually put some constraints on the theory? And the answer actually is in the so-called WKB method. It's a method actually was started for quantum mechanics to compute energy levels, but it can also be applied because the structure of the equation is the same, so to the computation of quasi-normal modes, and actually relates the frequency to the values of the derivatives of the effective potential at the peak with respect to the tortoise radial coordinate. So the first order WKB method only has the value of the potential at the peak and its second derivative, but then you can add corrections, and each of these corrections will introduce higher and higher order of derivatives of the potential. And you actually, so knowing that the alpha corrections so small, you can actually link the potential at the peak. So the pth derivative of the potential at the peak with that of GR plus a linear modification of it. And again, these delta VK coefficients will be universal. They can be computed. They actually look like this, as you see in the plot. And so now we can try to play the same game for constraining this sum here. So the modification, the displacement of the potential at the peak with respect to GR. And this is what we got. So each panel shows the displacement with respect to increasing derivative of the potential at the peak. The left-hand side shows the posterior distribution, while the right-hand side shows the prior. So you can really compare that for V0 and V2, there is actually some gain in information from the prior to the posterior. Whereas for V3 and V4, with the assumptions that we took for this case being, we don't really gain much. Okay, but at least you can see that, so the red line corresponds to the injected value. You can see clearly that for V0, you can really pinpoint that there is some deviation from GR and actually reconstruct it well. And also for V2, I mean, it's not super clear, but you see a trend for that. And also, like, if we compare it to what was the case of the alphas, it really looks much better. So in some sense, it's saying that this reconstruction of the potential is really sensitive to what is happening at the peak, which is a well-known result for quasi-normal modes, that they are actually originated at the peak of the potential. So this is, I think, an interesting way to actually prove it. So these are the conclusions of the talk, the bullet points with the questions that have been answered throughout the talk. And thinking about the future, I would say that the main limitation to what I've shown so far is that it was only for spherical symmetry. So it will be way interesting to extend it to the rotating case, because actually the black holes detected by LIGO, Virgo, and Cagra are rotating during the ring down phase. So we need to do it for spinning black holes. And once we have it, we can actually really apply it to real data, not injected things. And I also have this separate question, but still very interesting. It's like, can we really separate if we see something, are we able to separate the contribution of the background from the fact that the theory has a different dynamics? So these are all things for which I'm working on at the moment, and I would be interested to develop. And I think I'm done. Thank you for the attention.
Thanks, Nicola, for this very nice talk. Now we think we can ask some questions to Nicola. So yeah, I see one hand. Naritaka Oshita, can you please unmute yourself and ask your question?
Thank you. Thank you for the nice talk. So I have one question. So do you have something challenging to extend this idea to the case of rotation, the curvature?
Yes, I have some ideas. I'm actually working on that at the moment. I don't know if you're familiar with the recent literature on the topic, but there were some papers that came out in last May, I think, where they actually show how to derive a modified Teokovsky equation for alternative theories of gravity in the case where the coupling is small. And I don't know if you are familiar with these papers, but yeah, actually, in these papers they don't show the equations. They just write down a general form of the equation, but they don't write it down in coordinates. So I would be curious to see how would it look like if they have a similar form and we can actually add now a similar contribution like this, but to the Tokowski equation. And
okay, so assuming we have detected the fundamental first overtone and second overtone, then can we reconstruct the Tchaikovsky equation or something like that?
I don't know. This is something I would be interested in. I mean, for sure. So I know that you can apply this this formalism for slowly rotating black holes, and then crank up the spin. So using the spin as an expansion parameter for the alphas.
Oh, I see.
This is like the zeroth order of what you can do.
You are concentrating only on the slowly rotating holes, and then the
No. I would like to do an equivalent, but with the Tchaikovsky equation. So because this is like Reggio Wheeler or Zerilli, but in principle you can do it with the Tchaikovsky equation.
I see. Yeah. So one thing I have a comment on that. So the quasi-normal modes becomes long-lived as we consider highly spinning black holes. Yeah. So many tones are long-lived. So that's why I think it has an advantage. Yeah. So, but non-spinning black holes, the overtones are quickly decay, so it's very challenging to see, in realistic situation. So No, this is true, but like for the LIGO detections, I think the spin of the black holes that they see, it's around 0.7. So it's high, but I don't think it's sufficiently high to have like these long-lived modes. I think they appear closer to the Kerr limit, if I'm not wrong. Yeah, for example, if you suppose the LISA, if you look at the ring down out of the supermassive black holes, some of the supermassive black holes have very high spinning black holes of around 0.99. Depending on the model of the accretion disk around the black hole. So so then in such a situation, the tones are more long-lived than we see in the black hole of 0.7 spin parameters. So
that would be super cool to see.
Okay. Thank you very much.
Thanks to you.
Thank you.
There are questions from Tianqi Zhao. Can you unmute yourself and ask your question?
Yes, I have two questions. First, when you solve this Zerilli equation, did you include the spin or the rotation of the black hole as well?
No, as I said, this is only for spherically symmetric case.
So if you have a spin, or if the mass has a measured uncertainty, will it change your infer for the this non-GR effect? Can it play a role?
Actually, so thanks for the question. This is something I didn't say just to not enter in technicalities, but here when we define this likelihood, so here we know that R0H depends on the mass of the black hole. So because R0H is basically 2m. Okay, and we can assume that we have inferred the mass of the black hole from some in spiral merge and ring down simulation. So we have it somehow, but with some error. And what actually we did with the likelihood was to marginalize on this mass. So there is some error that is coming here is actually by the fact that we are assuming like a 5% error on the detection on the measurement of the mass.
Thank you. That is explained. And my second question is the way you introduce this modification of the theory, the potential. Is it the only way to introduce a non-relativist and non-GR effect, or is there other ways to include that? As George just said, possibly in F as well.
Yeah, but if you can always transform. So if you sorry, no, it's here. If you introduce some modification in F, then you can always change your variables. And so, for example, I think if I remember well, you have to divide phi by the square root of 1 plus the modification that you are adding to F.
Mhm.
And then if you expand, if you assume that this modification is small, and you rewrite your system with the new equations, then this term will go away and it will enter in Vij.
So here
So
the
you
phi
can always.
is it still considered the regular metric function we use in GR, or it is like a different field or something you just mentioned, like many fields? How do I understand this field? Is it the metric field that in spherical geometry, GR?
So yeah, they can be, for example, the Regge-Wheeler field. So the one that is coming when you write down the perturbation equations for
so
GR.
that's the regular. Okay.
Yes, exactly. But then in alternative theories, this can be coupled to other fields.
Okay.
So for example, if you have some scalar field, this will transform as a polar field, so it can couple to the Zerilli field, for example.
Okay, got that. Thank you. Yeah, it's very.
You're welcome.
The next question by Mikhail Malkov. Okay.
Yes, thank you. Can you hear me? Hello?
Yes.
Yes, we can hear you.
Yeah. So it's interesting talks. Thank you. The question that I have, if indeed you just get rid of F by taking integral dr over F and put it into the last term, then you have this standard Sturm-Liouville problem in canonical form. And then the first question that arises, particularly if you want to apply WKB, then where are the turning points of this potential and how the Stokes lines on the complex R plane are actually arranged, because this should define the spectrum. And how many turning points do you have in this problem? Because AG is not directly shown. I mean, the signs of these alphas, etc.
Yeah, but the key assumption is that these alphas are small, so you can always expand perturbatively in the alphas. And actually, this percolates to the location of the turning points. It is not modified with respect to GR, as long as the coefficients are small. Of course, if you take like a large enough coefficient, you can spoil the location of the turning points, but then the assumption for which this formula holds will not be satisfied anymore. So you cannot really rely on your assumptions.
But you still need to have these two turning points, right? In order to get
yes, but because you have, this is something you have in GR, and just by adding this combination here, it will get some small displacement away from GR. So the shape overall of the potential is the same. It's just a bit moved towards the right, towards the left, higher, lower, but the turning points are still two, and there is still one maximum only for the potential.
Fair enough. Thank you.
Thank you.
Any further questions for Nicola?
Can I ask about this linearization again? So it's the linearization doesn't work. So since this is spherically symmetric, I can imagine like two black holes in a head-on collision, so there's no spin. And so the idea, if I understand correctly, is once that dies down to the point that you're only looking at quasi-normal modes, then this is the picture that you're looking at, right?
Yes.
So how long after a collision like that do you have to wait to not be polluted by non-quasinormal modes?
This is like the question. Like there is a lot of people who are studying this. It really depends on on what you assume. So for the fundamental only, usually it scales like it's 15 times the mass or 20 times the mass of the final black hole. So after that, you're sure that all the nonlinearities are dead, and only the fundamental mode is still surviving.
Okay.
Because all the other overtones, the way that these frequencies omega they scale is that when you increase the overtone, the decay time decreases. So they actually decay very quickly,
right,
the overtones. But then the fundamental mode has a decay time much larger, so it can survive for a while. So what people in LVK do for now, they just know that at some point there is the fundamental mode and you can determine that. But of course, if you want to do tests of GR, you need at least 2 modes. So there is a debate on when actually you can start the first overtone, for example, because if you are too far from the real start time, you might be missing something. But if you're, I don't know, too close to the peak, you're just polluted by nonlinearities.
right. Okay, and yeah, so then that means you have to wait for like tens or hundreds of milliseconds for like a 10.
Yeah, actually, so what people do is actually to set the start time as a parameter to be inferred,
right,
and to try to trace it. But there are subtleties there as well. But
thanks.
Okay. If there are no further questions, then let's thank the speaker again, and we will meet next week.
Okay, thank you.
Yeah, that's great. That's good. Okay, great. So I don't know if you know our guest here. I'm Wick Axton. This is Sherwood.